Hi friends, welcome to GMK tutorials. In this video, we are going to start about the small signal analysis of a transistor. Okay, so if you want to represent a small signal model or maybe RE model of a transistor, so how it is possible? So how to represent a transistor model in RE model or maybe small signal analysis pointer. So for that purpose, let us move on to the topic. So before starting this topic, just I have a small request for you. In case if you are not subscribing our channel, so please subscribe our channel for latest videos. Okay. So small signal analysis point of view, let us see in case of the just a brief recap about the diode point of view. So in the last video, we see different types of the VI characteristics of a diode in different situations. Suppose so this is a IV characteristics of a PN junction diode. So this is nothing but diode current. So diode voltage. This is a one graph. At the same time, this is diode is non-conditioned. In case if the diode is also connected in a circuit or maybe a closed switch, at that time it behaves as a some Q point, right? I think all of you having this basic idea, right? So at the same time, suppose if the diode is in piecewise linear model, piecewise linear characteristic model, so it represents piecewise linear characteristic model, it represents just like this. So this is generally called a piecewise linear model. So the smallest change is generally called as the slope of this one. Okay, the slope represents a resistive behavior. Okay, the slope represents a resistive behavior. So wherever the corresponding diode starts a conduction, this range is generally called as a V gamma. So we can also call it a cut-in voltage of the PN junction diode. So this is generally a diode current. This is generally called as a diode voltage. So this is generally called as a V gamma. Suppose if you want to represent the equivalent model for a diode, so what is the representation of this equivalent model for this one? So V gamma plus resistive nature. So this is the equivalent. Suppose if you want to represent, this is the V gamma, so plus or minus V gamma and resistive. This is the equivalent circuit for a diode. Okay. Suppose if you are taking an ideal diode, the ideal diode starts with a 0 onwards, right? So at that time it represents only V gamma only. Okay, so V gamma is eliminated, therefore it represents only RD, or maybe that is nothing but dynamic resistance of the diode. Okay, so this is just a brief recap for a PN junction diode pointer. So that means if the diode is connected in a circuit, at the time it behaves as a resistor. PN junction diode behaves as a resistor if you are connected in a circuit. That is very important point noted here, right? So let us move on to the topic. So in case of a small signal analysis point of view for a transistor, let us see transistor point of view. So before we will have just a small basics related to transistor. So in case of the article of having a basically transistor, so transistor is nothing but a back-to-back connection of a PN junction diode. It is consisting of a base, emitter, collector. So base is lightly doped material, emitter is moderately. So there is some criteria will be there, obviously, right? So base is lightly doped material. So C is nothing but which collects the electrons. So emitter is nothing but a highly doped material. So so these are all the basics already covered in our in EDC subject, right? So in terms of sizes point of view, the base is size is very less. So it is also moderately, it is also very large size. So why? Because collector is very large, means that obviously in case if you are collecting the electrons in a collector region, obviously there may be chances of collisions. Due to the collisions also, there will be some heat will be generated in the collector region. So if you want to cool the device, or if you want to dissipate the heat to the environment, at that time obviously if the size of the collector is high, therefore obviously the device is also not quickly heated, because of the collisions and all those things can be performed in the collector region. So this is all about the basics point of view. Just I don't want to go through this one. So in case of if you are taking a transistor point of view, so this is generally a symbolic representation. Suppose if you are taking a NPN transistor, so this is a notation where this arrow represents the direction of the electrons. At the same time, this is generally called as a base region, emitter region. This is a collector region. So this so this is generally input side. So input side. So suppose if you are taking like this is the output section, right? This is the input and output section. So here the input is nothing but it is connected in between. The input is nothing but between base and the emitter region. So this is generally called the VBE. VBE is nothing but base emitter voltage. So in this case, this is nothing but, in this case, the second region is generally called as a VCE also. So this is also having a VCE, okay, collector emitter voltage, so base emitter voltage. Okay, suppose if you want to draw the characteristics, means that input characteristics, means that, so this current is generally called the IV current. Okay, this current is generally called the IC current. This current is generally called the IE current. Suppose if you want to draw the IV characteristics of the transistor, input current is nothing but, here the input current is nothing but, okay, so just this is for a CE configuration. Suppose if you want to represent a transistor in a base emitter junction, suppose in a CB configuration. CB configuration means suppose this is a representation, right? CB configuration. Suppose base emitter collector region, like base. So this is the connection. So in this case, emitter current is the IE. This current is the VBE. So this is nothing but VCB. So that is the representation. Just if you are taking in that point also. So let us see in this case general point of view. Just let us I will take this is the characteristics of a transistor. This is generally called the input characteristics and output current. So this is generally called the input characteristics of a transistor. Input characteristics means that the characteristics between the emitter current and VBE. Okay, at that time you need to keep some constants, that is nothing but, let it be take VCB1, VCB2, VCB3. So that means if you are maintaining a constant collector base constant VCB, that is nothing but collector base voltage makes as a constant. If you are increasing the VB voltage, obviously the graph also represented like this. If you draw the load line, it is also similar to the, if you draw the tangent, at that time it behaves as a piecewise linear model. Obviously it is also represents some resistive nature. So it is also similar to the PN junction diode. At the same time, if you consider the output side of the transistor, output characteristics means in case of the CB configuration, especially CB configuration, common base configuration. So base is common to the input at the time. So emitter is the input current and the collector is the output current. At that time, so that's why in case of the input side, emitter is the input current and VB is the input voltage. So this is nothing but input characteristics. So here also same thing in the output side also, the collector and VCB. Collector and VCE are the voltages. So therefore the graph versus collector current and VCE, collector emitter voltage. So this represents the output characteristics. So these are the output characteristics. So in this consideration, if you are making a IE value is a constant, even though if you are increasing the collector emitter voltage, the IE makes as a constant. That means if IE makes a constant means that it represents a constant current source. It makes a constant value of current means that it is generally called a constant current source. Okay, constant current source. So due to the early effect in the transistor, the graph is little bit like this. Therefore, if you observe this one, there is a small changes in this one. So therefore, it behaves as some resistive nature. So it is nothing but some resistive nature. It represents some slope. So if the maintaining curves represents a slope, means that obviously it is nothing but a resistor. Okay, it represents a small resistive nature also. So from these characteristics, if you want to identify the REAC point of view, let us see here. REAC, dynamic resistance. Dynamic AC resistance is directly proportional to the 1 by IDQ. Okay, IDQ for a diode case. At the same time, RE is directly inversely proportional to 1 by VT by so just wait. R is inversely proportional to RE, that is nothing but emitter resistance is inversely proportional to VT by IQ is equal to, we can also call it inversely proportional to 1 by IDQ. That means diode quiescent voltage, IEQ. Okay, so that is also very important. So RE is nothing but where emitter resistance. So RE is nothing but it represents a emitter resistance. So the curves represents a constant value, right? So this constant value represents the current, IE current. This is nothing but IE1 or maybe IE2 and IE3. That means the emitter current maintains a constant value. So wherever the network or it may be any circuit which produces a constant current value, that is generally called a current source. We can call it a current source, right? So that's why the emitter, the transistor represents like this. So if you observe very clearly from these 2 points, you have some idea from this configuration. In the output side, it behaves as a constant current source. It behaves as some constant current source. So that's why I can represent like this. So constant current source. This constant current source is proportional to alpha into IE. Why it is alpha? In case of the CB configuration, base is common. Therefore, alpha is equal to IC by IE. Okay. Therefore, this generally in case of the collector current. So in case of a transistor point of view, if you have observed this one transistor where so this is nothing but sorry, it's not a VB actually. This is a typo error. So it is not a VB. It is the output section, right? So it's not a VB. Just sorry for this one. These are all the outputs, right? So this is nothing but IC and VCE. So these are all the output section, right? So if you are, that means the output point of view, the current is nothing but a collector current. So that is nothing but a IC current. So therefore IC is equal to here alpha into IE. So this is all existing in case of the forward active region only. Forward active region. So active region means that, what is the active region? Active region means that the diode is an active region means that emitter base junction. Emitter base junction is in forward bias. Collector base junction is in reverse bias. Then only it is called as a forward active region. In a forward active region only it makes as a constant current source. That is very important. So that means it maintains some constant value, constant current source. So actually, but ideally it is a constant current source. Due to the early effect, it represents a small slope nature. That means that small slope is also represents some resistance. That resistance is generally called the output resistance. Okay, that resistance is generally called the output resistance. Here also the RC value is directly proportional to the ICQ. Okay, RC is directly proportional to, inversely proportional to ICQ. So R is RC, that means collector current is inversely proportional to 1 by ICQ. Okay, at the same time R0 is equal to it is also R0 equal to output resistance R0 equal to VA by ICQ, where VA is nothing but early voltage. Okay, therefore due to the slope nature it is also having some resistive nature, that is nothing but some resistance. I can call this resistance is a R0. Okay, this resistance is generally called as this resistance is generally called this resistance is generally called as a R0. So I will represent a small R0. So this is a small signal representation for a transistor point of view. Suppose if you are combinedly representing the input and output characteristics of a transistor, let us see. Okay, combinedly representing this one. So this structure is like this. Okay, if you are combinedly representing the input and output characteristics, the small signal analysis of a transistor is similar to like this. So this is a one source. So this is a small signal model of a transistor. Small signal model of a transistor. So let us see here. So this current is represents IC current, that is nothing but beta times that of IB. Okay, beta times that of, in case of the just this is a model for CE configuration. This is a model for CE configuration, base, emitter, and the collector point of view. Okay, so in this case, so emitter is a common value, therefore this resistance is also called as a RE resistance. This resistance is generally called as output resistance. Okay, so this is just a small signal model of a transistor. So that means if you want to represent in a small signal analysis point of view, internally this part can be represented like this. Internal part of this one can be represented as a corresponding this one. So why it can be represented like this means that basically, so this is nothing but base emitter. So if you are taking a NPN transistor, this region represents a PN junction diode nature. So this part represents the input side represents a PN junction diode. So the PN junction diode is also nothing but it represents a one kind of a resistive nature. Therefore input, this part is represents a PN junction diode, therefore it can be represented as some resistive nature. Okay, so at the same time this output side can be represented as a constant current. So this can be act as some IC current, therefore it can be represented as some constant current source. But practically this constant current source is also a small variation in the slope due to the early effect. It is also maintains a small slope nature, therefore that's why it can be represented some R0 in a practical consideration. That is nothing but RE. This is a small signal model of a transistor. It's very important. It is also called the RE model of a transistor. Okay, suppose if you want to analyze a small circuit, small signal analysis point of view, you need to calculate the gain, right? Okay, so let us move on to the next one. Suppose if you want to find out a small signal model for this circuit, so let us see here. So in case if you want to find out a small signal analysis means that we can if you want to find out a small signal analysis, first of all you have to find out the AC equivalent circuit. That means if you want to find the gain of the amplifier, if you want to find out the gain of the amplifier, so if you want to find out the gain of the, if you want to apply a small signal to this transistor, obviously suppose if you want to apply a small signal, this one, small signal is nothing but the variation of the input signal is very close to the VB voltage, changes in the VB, or else a small signal refers to the signal in the range of millivolts. Okay, it is in the form of millivolts or maybe microvolts to millivolts. Then only we can call this a small signal. Okay, like a sensor signal, voice signal, these are all in terms of a small signal point of view. In case if you want to transmit a signal through a transistor, it does not allow the small signal directly through a device. So if you want to allow the corresponding small signal, first of all you have to keep your device in a quiescent point mode or maybe operating condition. So for that purpose only we are applying a biasing voltages like RB, RC. Okay, these are all generally called the biasing elements. These biasing elements act as a to set the Q point of the corresponding transistor. Whenever the Q point is set in the corresponding transistor, it behaves like some resistive nature. Therefore, the corresponding AC signal can be passing through the transistor without any degradation. So that's why first of all, whether it may be diode or transistor, first of all you have to set the Q point for the corresponding devices, then only it supports the AC signal or small signal. Okay, that is the small signal is nothing but the basic difference between larger signal and the small signal, just in terms of difference of the voltage only. So the small signal may be around in the range of microvolts to millivolts to mention. Okay, so that is all about the some of the basics. Suppose if you want to find out the small signal for this one, first of all, so there is some important conclusions here. That conclusion is nothing but, so these capacitors can be short circuited. Okay, so current source can be open circuited. Voltage source can be short circuited. So these are the some of the assumptions we have to make if you want to find out a gain of the transistor. If you want to represent the equivalent model of a transistor in a small signal point of view. Okay, that is very important, right? So for that purpose I have to represent it here. So if you are replacing the corresponding capacitors can be short circuited, then it becomes as a circuited like this. Now the small signal can be represented based on this is the AC equivalent circuit, right? Now if you want AC equivalent circuit, now the equivalent circuit for this one, okay, the equivalent circuit for this one in case of the RE model, just there is a small variation. This is very important, guys. Just if you know the basics very clearly, it's a very easy thing. Just you don't want to compromise at all. Okay, just I have to represent the RE model for this one. Okay, so let us see here this part, whatever this part, this is the input section, right? This input is nothing but similar to this PN, so PN junction diode. So that means this is also act as a PN junction diode nature. Therefore, it is also act as a resistive nature. Therefore, that's why I can call this a resistor in the emitter side. So that's why I can call this a RE. This is the input section, right? At the same time, this represents generally IC is nothing but a constant current source. Therefore, it can be represented as a constant current sources. So it is a dependent source, dependent current source, dependent current source. That's why it can be represented as a beta into, so in terms of beta into IB, beta into IB. So this is also here beta into IB. So it is also connected to the some resistance. So here also some resistance. That resistance is generally called as a RC. Okay, that resistance is generally called as a RC. So from at the same time, from input side also you have one more resistance, that is generally called the RB. This RB also connected to the ground, so it is connected. So this RC is also connected to the ground. Therefore, it can be represented as like this. So this part is generally called the input. So this is nothing but equivalent model of a transistor in a small signal point of view. So this is very important consider. So here we don't have any node drop. So node drop will be takes place in case of the transistor, in case of the AC signal. Why? Because if the transistor in the linear region or maybe forward active region, it behaves as a current source. At the same time, if the transistor is operating the Q point, if the transistor is operating Q point or maybe operating condition, it behaves like a linear nature. The linear condition or linear region, whatever the input, if you are applying to the transistor, it directly pass the corresponding transistor without any degradation. So that's why in case of the AC signal, no drop for AC signal, because it passes through the slope, both positive and negative passes through it. So that's why no drop will be takes place. But the drop takes place only for DC signals only. Okay, that is also very, very important point. Okay, so that is all about a transistor for a RE model, okay, or small signal model. Suppose if you want to find out the gain of a transistor, okay, if you want to find out a gain of a transistor, so for that purpose I will take one more example for this case. Okay, I will take one more example. Just we will find the gain of the transistor. So in the most of the current circuits also, mirror circuits also, we will find out the gain of the circuit. Instead, if you want to find out the gain of the corresponding circuit, you need to represent the transistor in an equivalent model. That means you don't want to go through any kind of the voltage sources and the capacitors in the circuit. That means if you are representing the AC model, means that no drops will be take place. If no drop takes place, obviously AC signal is passing through the device. Then only you can calculate the gain of the transistor. So without any degradation, you will get the output. Therefore, no degradation takes place. Then just you can calculate the corresponding gain of the amplifier. So it is very important. Last problem for this one. Just listen very carefully. So just I will take one transistor. Just for this one, some resistance, some capacitor is also there, something here also, some two resistance. These two are connected to AEC. These two are connected to. So this is a circuit diagram for this one. So for this circuit diagram, you have to represent a small signal, and you have to calculate the gain of the circuit. So if you want to calculate the small signal model, at the same time you need to find out the gain of the circuit. So this is, I will call it the C0, CA is. So if you want to represent a small signal model, first of all you have to short circuit this. So for the small circuit model, so voltage source is a short circuited, the current source is also open circuit. At the same time, the capacitors can be replaced with the internal values. That means capacitor is also short circuited. Okay. Therefore, for this one, let us see here. So just you have to represent this one in an equivalent model. Obviously, it acts as a short circuit. Okay, it is also acts as a short circuit. Just you have to represent individually. Therefore, it is a voltage source. So this can be represented as individually. Therefore, it is nothing but RB connected to ground. Okay. So this part, whatever this part is there, this is generally called as a. This part is generally called as a. Internally, it is a RE. But this part, whatever this one, base emitter, this base emitter represents a p-n junction nature. Therefore, internally it represents some resistance. Therefore, it is having some resistance. That resistance is generally called as a RE, small RE. Okay, at the same time the outside also it is also having a resistance Re, therefore it is also connected in a Re. Okay, capital Re. So here there is a small difference. Internally the corresponding circuit behaves as a PN junction diode. So in a small signal model, PN junction diode is act as a some resistance. So Re. So this is nothing but capital Re. That is very important. At the same time, output point of view. So this region, whatever this region, this is generally called the IC region. So here it acts as a constant current source. So constant current source. It is also in a CE configuration. CE configuration. Collector is the output current. IV is the input current. Therefore, IC is equal to beta times set of IC, beta is equal to IC by IV. Therefore, IC by IV is a collector current. So here the IC by IV is a collector current. So this is only internally for this part only, but externally it is also having some resistance RC. Therefore, you need to connect that RC to the ground also. So RC. So this is a equivalent model representation for the circuit only. I think it's very easy, guys. Okay, just input section can be represented as a resistance, and you have to add, in case is there any resistance, these two resistance connected in a series fashion. So this output section acts as a constant current source. Is any resistor, just you have to connect it to the parallel. Why? Because current source and corresponding values are connected in parallel only, right? So that is a representation model for this one. Now if you want to find out the gain for this one, gain of this one, just see here, from the input section you have to apply the KVL. For the input section you have to apply a KVL. Vi is equal to, so for input section you have to apply a KVL. Therefore, input voltage is equal to, here input voltage is equal to drop across Re, that gives rise to overall voltage. So here we don't have any current, therefore it is equal to 0. So let us see here. So for this case, therefore input voltage in that circuit, Vi is equal to 0 plus, okay, 0 plus the current passing through the that one I into, okay, suppose just in this case of it, just I have to take only, I don't want to consider normal considerations only, okay, Vi is equal to I into input current into Re, internal resistance plus external resistance Re, right? So from this, Vi is equal to Re plus Re. So it is also, we know that generally a collector current is also approximately equal to emitter current. Therefore, I have to replace this complete current with in terms of IC. Okay, therefore it is equal to I into IC. So at the same time it is equal to RC only. Okay, RC. Therefore now V naught by Vin. Now you have to find out the output value. So this is the input section, right? So therefore output side, output voltage V naught is equal to current passing through the corresponding circuit into RC. So it is a, so here the negative sign is always represents opposite direction. Okay, so V naught is equal minus, okay, minus I into RC. Therefore you need to calculate the gain of the circuit. So gain means that obviously AV is equal to V naught by Vn. Therefore output voltage minus I into RC by, so this completely equal to some current entering into this one. I is equal to obviously I is equal to RE plus capital RE. Okay. So these two get cancelled little bit. Therefore, you have a negative sign is also there. Therefore, if you are taking RC value is approximately equal to RE, that means collector resistance is equal to approximately equal to, not equal to, approximately equal to RE. Therefore, AV is equal to, voltage gain AV is equal to minus RC by collector resistance by minus RC by RE. So this is a voltage gain formula. Okay. So here the negative sign is because of current direction is opposite. Current is opposite direction. So that is a very important thing. So in all small signal models, you will get negative sign mostly in RE model, all those things, because of the current is entering towards the node. So that's why it is called a negative sign. Okay. So whatever the circuit, in case if you want to represent any circuit, whatever the circuit if you are representing, just if you want to calculate the model for this one, just I have to represent this just one basic diagram. So some correspondence RC. So we will let it be take 10K. So this is nothing but about 2K. Let it be like this 2K. Some base current maybe something like this. Whatever it means, just I will take 1K like this. Just if you want to find out the PA. Suppose if you want to find out the output voltage, output of the output or maybe gain of the circuit, just only gain V0 by Vi is equal to, what is the formula? So V0 by Vi is equal to, what is the gain formula? So that is nothing but minus, so collector resistance divided by resistance. So that is nothing but 10K divided by 2K, that is equal to minus 5. So the gain of this voltage gain is equal to minus. So that means if you know the basic concept, you can just directly find the voltage gain within a seconds only. So this is all about the transistor representation in case of the RE model. Okay. So the transistor behaves as a forward bias, it acts as a resistor. In the output side, it behaves as a current source. Practically, there is a small variations in the slope. Due to that, it represents a small resistive nature. Therefore, the resistance is parallelly connected to the current source. So this is all about a small signal model or RE model of a transistor. I hope this video is very useful. So thank you guys. Thank you.